Hi, guys. Thanks, everyone who joined this talk. If this is your first bug out meetup, welcome to the community. I shared a link to join our Slack, where a group of developers, data scientists, machine learning engineers. So please join and let's connect and just create this community where we share our knowledge, expertise, where if you are working on something, you can share about your work. If you have some technical challenges and you need support, you can also, request some technical support, like advice from our community members. And we're also organizing meetups with our amazing speakers, like Chandra Khatri, who joined us today. And today, we will talk about conversational AI and how it has changed and what further research we should expect, especially considering that transformer-based models, they really changed the landscape of NLP. And it's a really very exciting field to be in. So our guest, Chandra Khatri, he's one of the leading experts in conversational AI. Currently, he works as a chief scientist and head of AI at a company called Got It AI. And before that, he was leading research work at Uber AI. So thank you, Chandra. Thank you for joining, and we're looking forward to your talk today.
Thanks a lot, Sophia, for the invitation, and I'm glad I'm presenting in front of this community. So yeah, let's start with the presentation. So I'm going to talk about, as Sophia mentioned, I'm going to talk about how conversational AI has evolved and where it is heading towards. So about myself, currently I lead AI at Corrid, which where what we're doing is we're trying to transform conversational AI by simply making it very easy for anyone to build conversational applications without annotation. And we'll talk about that, what it means. But the idea is that currently the biggest limitation of conversational AI is that it requires lots and lots of data and human labels and human designing the flows. That is extremely inefficient. But that's where that is a state of the art in conversational AI. And we want to push that further. And that's what I do. Before that, I was leading conversational AI and multimodal AI group at Uber. I was also the founding member of Amazon Alexa AI, also Alexa Prize, I was leading it. And I mean, that's about me. But the idea is that I've seen this, how conversational AI has evolved, especially from classical machine learning to deep learning to now with transformers or more advanced semi-supervised or unsupervised technologies. And I will cover all of that here. So the agenda is, I will first give a motivation of why language understanding and why conversational AI, why is it hard for machines, kind of philosophical angle. Some might like it, some might not connect to it, but the idea is that we need to first understand what the problem we are dealing with. Once we know what problems we are dealing with in building conversational AI or NLP applications, then we will be able to address it better. So that was the motivation. Second one is I will talk about the components in conversational AI, what makes conversational AI, like what constitutes conversational AI system. Then I will deep dive on the evolution of the NLP technologies. Again, it will be more, it's not like I'm going to talk about just, it will be more deep. I will go deep into concepts and walk you through how technologies have evolved and where it is heading. And then I will give an overall perspective on what is the state of the art, where it is heading, and finally, the global picture of the entire evolution of conversational AI. So that is the agenda. So let's talk about the motivation, why language understanding or why conversational AI. So let's see why language understanding is hard for machines. Unlike images or driverless cars, they might seem equally hard, but they are not equally hard. They're much simpler problems because if you look at a driverless car, at any given point, let's say there's a red signal, the action which a car has to take is always deterministic. Like it has to stop, it has to stop. Once it identifies, once the sensors and images or once they identify that the speed, this is the speed, or this is the red light, or this is the signal, or these are the cars nearby, or if these are the objects nearby, the action is always deterministic. But language is not like that. However, the stakes could be high in driverless cars. But of course, if the car is not doing well, then it's people's life at stake. But in that does not happen with language. Actually, language is completely open-ended. So let's say if I ask a question of what do you think about Obama, all of us here will give different answers, and all of the answers are correct in their own regards. So to train a model like this, which understands this kind of ambiguity and is also able to generate this kind of responses based on the context, that is NP hard. Actually, it's NP hard AI problem, or in fact, it is one of the open-ended problems in AI. AI, in fact, considered as hardest AI problem. In fact, many people still think that it is the language which has made humans the most dominant species. Again, I don't want to go dive deep in there, but that is the level of complexity which is required in language, which is substantially easier in images or any other task. One thing with language is it is sequential in nature. So what I'm going to say next is function of what I've said before. Even let's say if I'm saying the same thing to different people, let's say here, if I'm giving a talk here compared to if I'm giving a talk somewhere else, it will change. The way I'm presenting will change. So there is context, there is sequential nature of it. There is representing language in mathematical form, again, is an open problem. Images are like every pixel is a number. So it anyway is a number. Like it is, you can simply feed in and then you don't need to transform it, right? But here in language, you have to transform spoken language, voice, or text, which is non-mathematical, to a mathematical form, and then make machines understand. That is also hard. And contextual, I talked about, like, for example, I can give an example of context. Let's say if I use word blue, blue can mean many, many things in different contexts. Blue could be, I'm feeling blue today, which could be a feeling. Then the sky is blue, which is color. Then it could be, I saw a blue whale, then it's animal. And in fact, I like drinking Blue Label, then it's alcohol. So depending on the context, the meaning of the word changes, right? But that does not happen with images, if you see, because a cat will always remain the cat. Like it will always, wherever you take an image of a cat across the world, they will know it's cat. So these are the different challenges of why language is hard. But once we know these challenges, we can address them. And that is kind of my approach of addressing conversational AI. So let's look at the conversational AI. What are different kinds of conversational AI systems? There are chatbots, which you might have encountered on websites, right? There are voice assistants such as Alexa, Siri, Google now, right? And then there is multimodal AI where, you might have seen devices, and those devices, you speak through those devices, but they're multimodal. One example is, let's say if I talk to Alexa, if it's Alexa Echo, a device without screen, if I say play Harry Potter, probably I'm referring to audiobook. Or if I say, if there is a Kindle, if I say Alexa play Harry Potter, I'm probably referring to novel. If I say, if there is Fire TV, if I say Alexa play Harry Potter, probably I'm referring to movies. So depending on the context, depending on the modality, the experience could be different. So these are the three broad categories of conversational AI experiences. Then let's look at the types of dialogue system. So one is task-based dialogue system. So you call customer support. Let's say I want to cancel my account, or if I call a bank, that is a task-based dialogue system because you talk to an agent and there is an objective, right? So there's a task associated with it, and you try to address that. So that is one category. Second one is, as I said, voice assistants. There is no particular task in this one. Sometimes there could be, such as, hey, Alexa, switch on the light, switch off the light. These are not multi-turn tasks. These are more assistant kind of relationship that you build. And over the course of time, it will be more customized for your experience. So it's more personal to you. Eventually, it will happen. And then there is more open-ended or open domain or non-task-based conversational AI system, such as, you might have seen Sophia, the bot. Basically, or there are some bots which are being built for building more engaging or natural or human-like conversations. Alexa Price was one of those which I was leading at Amazon. So the idea is to make AI which can talk to human on any topic about every topic, right? So that experience does not have a task. You start talking about, say, movies, then you go on talking about sports, then politics. That's how you chat with your friends, right? Or your family and whatnot. So that is how it happens. It's more natural conversations. There is no task. The objective here is to make the conversations more engaging and try to build that kind of relationship or social kind of relationship. So these are the three broader categories of dialogue systems or conversational AI applications. Now let's look at what are the components of building any conversational AI system. So when, let's say, if you take an example of Alexa, if I say, Alexa, are there any action movies this weekend? So I spoke, that is spoken form, right? Speech signal that has to be transformed into text. And that happens via speech recognition system, which is blue here. And you can see the reason why you want to convert that speech into text is because all the data in the backend, or the way we store the data in, or like in a machines or in a computers or databases, is actually in the form of text. So you have to convert that speech into text form, and therefore you need speech to text, that speech recognition. Second component is, let's say if I say, Alexa, are there any movies near around or in this weekend? Then the first thing which we need to do is, we need to understand, or Alexa needs to understand, what was said, what is the intent, what is the domain, what exactly is the user looking for. So the domain here is movies, then an intent here is to request movie information, and slot here is action movies, and maybe date is this weekend. So essentially you need to understand what is being said, right? And the way we do it is via domain identification, intent detection, slot identification. So that is all part of language understanding. Then the next part is dialogue management, wherein dialogue management is basically given the intent of the user, or given identifying what user want. Based on that, or based on the output of language understanding, dialogue management returns the response, or it identifies what exactly should the response look like, or what exactly is user looking for, right? So one is to identify, and next thing is what action to take, and that action part comes from dialogue management. So typically it communicates with backend actions or databases, and then you get a response. So given this question, dialogue management says request location, right? Meaning to find a movie on this weekend, the assistant or Alexa or dialogue manager wants to know where exactly are you located, because if you are located in, say, India is, or maybe Europe, that might be, the movies over there will be different from you are in US, right? So it wants to know the location, right? So then it requests location. But typically these databases, they store, you see the database or this dialog management returns a value called request location. You are not going to respond that user, the response will not be request location. Response will be more like, hey, where are you located? Or I want to know your location before I can give you recommendation. So the idea is that that part has to be converted into a natural language, which is meaningful, right? So that's where comes in natural language generation. It converts the output of the action, the dialogue management or actions, into responses, right? So these are the four primary components: speech recognition, language understanding, dialogue management, and then natural language generation. And this constitutes any kind of conversational AI application or system. Now let's look at we just looked at what problems we're dealing with. Now let's look at how technology can be used to address these problems. So let's look at the NLP and NLU technologies are foundational to building any conversational AI application. So if you go to classic NLP, if you want to convert any text into a mathematical form, let's say if the task is to do sentiment identification. So let's say if the sentence is Obama is the president of the United States, the sentiment is sort of neutral. So there is, for training any kind of classification problem, you need an input and also need a label. So label here would be 0, but the input here would be some kind of feature. And as I told you, text is not feature, text is not mathematics, text is not number. You have to convert that into number, then only your algorithms would be able to understand it. So to do that, the classic way of doing was called one-hot encoding, where you take all the words in the dictionary and they become features. So let's say if in your dictionary has 10,000 words, then you have 10,000 features, and whichever word is present in a given sentence, that becomes 1, everything else becomes 0. So it's called one-hot encoding. So in this setting, Obama is the president of the United States. There are 7 words, so there will be 7 ones, and remaining 10,000 minus 7 would be all 0. So it's a sparse matrix, and therefore not very efficient, and it does not account for context as well. So there are many limitations with this one. The biggest limitation here is that for smaller applications, they are okay. But when you tend to go at the scale of Google, Alexa, Uber, Amazon, the vocabulary is millions of words. Google, maybe hundreds and tens of millions of words, actually, maybe even hundreds of millions of words. In fact, I've trained model with, tens of, maybe hundreds of millions of words vocabulary model. So point is that you want to do that, and this will not scale. No machine in this world can fit in this kind of memory because the representation is too sparse. To address this problem in 2013, Thomas Mikolov at Google, he came up with this approach called embeddings. The idea is that we convert each word into some kind of embedding, fixed dimension embedding. So let's say if you take Obama as a word, Obama can be represented as some fixed dimension, let's say 300 dimension words or 300 dimension vector. And you can have that embedding. You can do the same thing for all the words in your dictionary or in your data. And let's take an example here. On the left side, it's 2-dimensional. Let's say if the dimension was 2 only, like X and Y. So what you're getting is you get feature representation or vector representation of each word. And typically the objective is to make sure the words which are close to each other, they tend to be closer in this dimension as well. So Obama and president would be close to each other. Speaks and greets would be close to each other. Illinois and Chicago would be close to each other, and so on. So the idea is that you want to come up with an approach of obtaining vector representation of each word, and each of these vectors should be meaningful, meaning that the ones which are close should, or the ones which can replace each other, the words which can replace each other, such as blue label versus red label, or blue sky versus pink sky. So sometimes they could replace. They can also replace in terms of meaning, such as blue whale versus shark. Of course, they both are different, but they are both water species, right? So they will be similar or very close. So that is the idea. But let's see how we get this embedding. Embedding can be of any dimension, but let's try how to get this, try to understand how we get the embedding. The way we get the embedding is this. We basically, let's say if the example was Obama speaks to the media in Illinois. So let's say if you want to get the embedding for word media, what you're going to do is you take the word, couple of words before word media and couple of words after the word media. You take that as an input and predict the word media. So it's basically a neural network where the input is context words, words before, words after, and you predict the current word where you want to get the embedding for. So once you do this, you pass it through all of your data, and this is the X, this is the Y, and eventually the vector just before prediction of Y is a representation of this word Y, or let's say media in this case. You can also do exactly opposite of it. This is continuous bag of word model. Another one is skipgram, which is exactly opposite. You pass the context word, let's say media, and then you predict the nearby words, right? Or context words. So that's called skipgram, but essentially they both tend to do similar things. So skipgram versus continuous bag of words. Let's look at what Word2Vec mean. Let's say if we train our model on some data, and if you see here that we get the embedding for each of the words, king, man, woman, queen, essentially because it's vector representation. If I were to subtract man from king and then add woman, then the embedding that you get should be tend to very similar to queen. And that's what they do. That's what we see. Basically what woman is to queen is actually king is to man, or sorry, man is to king. So that's how you tend to get, and that's what we see as well in the embeddings. But question is, are these embeddings contextual or dynamic? But no, they are not. Once you train your model, once you obtain your word embeddings, they do not change. They are not dynamic. They do not account for context. The embedding learned for word king, or let's say queen, will always be king and queen unless you update it. So even if you get the embedding for word blue, blue word can be used in varieties of contexts, which I've shared before, but the same embedding will go in all of the scenarios. But that's not contextual. It does not account for context. The embedding of word blue should change. That's how human mind works, we understand, and that's how also the meaning of words change. The context changes, therefore the way models consume this embedding should also change. But Word2Vec does not do it, and Word2Vec was state of the art till 2017. Then transformers, or maybe Elmo, which was RNNs based model, I'll come to that, happened to come. That was precursor to transformers. But over there, we were able to build dynamic word embeddings, meaning that the embedding of the word would change based on the context of the input. So let's see, the way we do this, obtain these contextual embeddings is through language models. Let's see what language model is. So language model, as the name suggests, it basically represents language, or what it means is it learns the sequence of words. That's how even kids learn language, or we as humans, we learn language. So let's say when a kid is born, first they tend to learn words like mama, papa, and so on, right? Then they will learn water and maybe food and stuff like that. But then they will tend to see mama water, papa food, and so on. So basically they are learning sequence of words by mimicking what they're seeing around. And that's what these language models do. Bird, GPT, or any kind of language model, they tend to learn the sequence of words which they have seen. So language model is nothing but being able to predict the next word given previous historical words. That is the idea. And we tend to do it. Any language model, every language model actually does exactly the same. There are nuances how we train them, but the idea of language model is this: predict the next word given historical words. But let's say how to train this. Okay, this from concept point of view, it makes sense, but let's say how to train them. So one of the first approach was recurrent neural networks. There are previous engram-based approaches as well, but most state of the art or till 2017, 2018 was RNNs, recurrent neural networks. The idea is that we, let's say if I want to predict the next word, and let's say these are historical words or there is some input, what you're doing is you keep track of the context, previous context, and then you use that context to predict the next word. So the back arrow here, which you see here, is basically the context from previous words or previous input, and that's how you tend to learn language models. Basically, one approach, of course, is to simply use feed-forward neural network, but they are not very powerful. The objective, the way of storing the context and then using, makes it much more powerful. In fact, if you look at the evolution of how memory and humans have evolved and any species have evolved, that is very similar. The idea of RNNs or neural network actually has come from here. You see the way there is not much difference between the cells that we have and an amoeba. Some nuances, but typically the structure is very similar, just that we are much more complex because we have more number of them, more number of neurons, and therefore we are able to capture and store more information. Therefore we make it more complex, but essentially the fundamental unit is same. Second thing is they are sequential. So DNAs, RNNs, ATCG, all these even in DNAs that we have, essentially these proteins are nothing but they are memory in sequence, and therefore that makes it much more complex because it can store more information, and because it can store locally and globally, it can perform contextual tasks, which leads to more intelligence or higher intelligence compared to other species. That is the only fundamental difference, nothing else. So that's how we do it. We basically are able to capture contextual information or store that in memory or in longer sequences, and with that we are able to take or remember actions and maybe make more informed decisions compared to other species. Let's look at now that was again philosophical, but let's look at an example of machine translation. Let's say the objective is to translate from French to English. There is typically an encoder RNN and there is a decoder RNN. So what encoder RNN means is that it encodes the input. RNN is the neural network which I just showcased. So encoder RNN encodes your input and gets you an embedding, right, which you see here. So whatever the input was in French, probably you pass those words, encoder RNN will feed that and then finally give you an encoding. So each word goes into RNN, and RNN will give you, based on the context, it will give you an embedding. And then decoder RNN will then decode and then generate the word. So it takes the input and then generates first word and then uses that one to predict the next word and then so on. So essentially, again, it's language model. This is also a language model. This is also a language model. This is an encoder language model. This is a decoder language model. And it's like encryption, decryption in a way. But the idea is that once the input is fed, you get a good representation and then you use that to decode your output, which is the translation task here. But question is, are these the best? Is this the best approach, or maybe the most powerful approach? Maybe not. Reason is you tend to get only one embedding for this entire sequence, which sometimes is not enough. In fact, it could do worse. Let's say if you were to doing English to Arabic, probably it will do worse because Arabic is written right to left, but English is written left to right. So probably the first word, the last word here in English would account for the first here in Arabic, and therefore English to Arabic translation would do initially for the initial words, it might do well, but for the words in the end, where the last word here in the Arabic accounts for the first word or initial words here, and therefore it's the sequence being too big, it will lose the context, and they don't tend to perform well. So to address that problem, we came up with something called attention. What attention means is that same input, encoder RNN, the only difference is that we keep track of each hidden state. So if you pass first word, let's take a pause here. Let's say 3 words were passed, and therefore you have 3 embeddings. We store all 3 instead of getting 1. We store all 3, and then the decoder RNN or the attention decoder RNN will use all of them. It can use all of them, but how would it know? Is this one important, or this one important, or this one important? So that comes from a matrix that we learn called attention. The idea is that automatically a model will learn that probably decoder at time step 1 should give more emphasis to, in case of English to Arabic, a timestamp one should give more emphasis to this last node. In case of Arabic, again, the last time step should be accounting for the initial node here, the first one, because it's written right to left, right? So the idea is that we learn this metric, or we learn this weight matrix, and this weight matrix is nothing but attention. What it means is that at each decoding stage, or decoder RNN will tell you, or will get to learn what weight or what embedding or what hidden state to emphasize on from the input. And that's attention, and which makes it much more powerful compared to a classic RNN based encoder decoder RNN. So this is state of the art till 2018, but this also became the basis of the this also became basis of transformers. If you look at the transformers first paper, it's called attention is all you need, and that's what they did in transformers. They came up with a better approach, and I will explain what that means. The idea is that transformers have these 4 building blocks, and attention, where it has all of the attention. They are contextual. Remember I told you that the word blue in different contexts could mean different thing. Even RNNs are not great in capturing that, but transformers do. Through attention, they do it. They're much more contextual. They're dynamic in the sense that the embedding for word blue will change at every based on the context. So they're contextual in that way, and they're autoregressive, meaning that the prediction at time t plus 1 is function of prediction at time t. I will show what that means. Transformers are also more scalable, and this is the biggest differentiation between RNNs and transformers. RNNs is a horizontal architecture, but transformer is vertical architecture. And being let me show you that through diagram, and then you will know what exactly it means. Point is, transformers can be scaled to billions of parameters because it's vertical. Therefore, you simply keep on adding more and more compute to it. Let's say if Google wants to train a model with hundreds of billions of parameters or trillions of parameters, what it needs to simply do it has to simply spin off a cluster, and each cluster is running one transformer block. And the more number of transformer blocks you have, the more parameters you have. And that's what GPT-3 did. T5, BERT does not require as much, but that's what these transformers actually do. So let's look at dynamic part first. Attention in case of transformers, as I told you, that in case of RNNs or RNNs with attention, once you train and obtain attention, they don't change. But in case of transformers, attentions are computed in real time. So let's say if they input blue whale versus blue label versus feeling blue versus blue, blue sky, based on that, based on the input of the sentence, we are going to compute the embedding. So the embedding keys and values, and also the attention values. These will be computed dynamically. I'm not going too deep in this because of time, but the idea is that we get these embeddings dynamically, the attention values as well as the word embeddings. And that was the attention part. Wait, that was dynamic attention. And again, this is the autoregressive part here. As I told you, that when transformers to predict the next word, they tend to account for previous words. So basically, whatever decoder has generated so far, it will efficiently use previous words and then generate the next word. That even RNN used to do, but again, decoders in case of transformers, they do it much more in much more efficient way and much more powerful way, actually. So and as I told you, that they are more scalable. Transformers are. So let's look at why they are much more scalable. So this is the state of the art till 2018. It was Elmo obtaining. It is RNN based, or LSTM is RNN. Elmo was state of the art till 2018. The idea was that we will get embedding which are more contextual based on the input, but the problem is that they're horizontal. RNN is horizontal. As I told you, as I showcased you, that RNN word or RNN state, it's function of the previous context, and also it's function of the input itself. So what happens is that if you look at the arrows here for prediction of the, let's take this LSTM. The problem with this LSTM is it has to always wait till the previous one is computed. Or in a way, what is happening is, let's say you have to fit this entire thing in memory, because you will need to have all of these parameters available in your model or in your memory, and then only you will be able to predict it. In contrast, if you look at GPT, which was one of the first transformer-based model, it was even before BERT actually. What happens is it is more vertical, meaning you have one transformer block, you have another transformer block, you have another transformer block, and you can add as many as you want, depends on how much money and resources you have. The idea is that it is vertical, meaning that given your input, you will get different, you can have different transformer block on the input, and they can run in parallel on different machines, or different clusters. The horizontal part here is actually not in the same time. I mean, it's basically a function of the previous one essentially. So even though there is horizontal layer, but it is coming from the previous one. So therefore, by that time, this one might already be computed, and therefore it will make, you can scale them up. This one does not have to be blocked on this one, or you can have varieties. You can have many blocks of transformers running in parallel, communicating with each other, and therefore you are able to make the results much more powerful. Now let's look at the difference between GPT and BERT. GPT actually is, as you see here, it's a decoder. What it is doing is it is using the next, or let me see, it is predicting the next word given historical words. It does not account for, let's say if I want to predict this word T2, it never leverages any of the future words or future encodings or any of the future values from other transformer blocks. What is happening is it only uses historical ones, and therefore it is trained to predict the next word in the most optimal way. Therefore, it is a decoder or the purest form of language model. But on the other hand, is not the purest form of language model. They train used via masked language model. The objective is that the future words or future encodings could update your previous embeddings or the previous embeddings in the previous states. So let's say if the input is, if I want to convert some sequence, let's say French to English, the BERT is not a great model, because what is happening here is that it tries to predict the next word or the next, in real time. BERT is not the best model, because it is trying to get a good embedding output or get a good word out at time step 2. It has to depend on, or it depends on the future words, which it might not have seen so far. So BERT has a requirement. It requires the entire sequence, or it has to see the entire input before it can make prediction. And that limits BERT in terms of generation task, and therefore BERT is not a great generative model, but it is a great encryption model or great encoding model. Because GPT is not a great encryption model or not a great encoder model, because it does not account for future words. It only accounts for generation. So therefore, there are nuances here why GPT is great generative model and therefore used for summarization, question answering. BERT is not as good. BERT is great for classification, tagging kind of task. And I will walk you through some of the example as well. And there are lots and lots of transformers, as you see here. Albert, XLNet, BERT, XLNet, BERT. So there are two directions in which research is going. One is more and more parameters. Like GPT-3 was 175 billion parameters, which is nearly 1,000 times the BERT model, the first BERT model probably. And then now we have even 10 times bigger model from Google, T5, or T5 with switch transformers. That is 1.7 trillion parameters. So you see, there is one direction which is adding more and more bigger models and then making it accessible for everyone. Another one is computing and summarizing some of these models, or not summarizing, basically distill through distillation, or basically leveraging the same bigger model or same ideas and compressing them into smaller models. In fact, I remember Sophia yesterday or day before yesterday showcased GPT, some variant of GPT, which is 6 billion parameters, probably doing similar task as 175 billion parameters of GPT-3. So basically, there's one idea of minimizing or compressing bigger models into smaller models, and another one is adding more and more transformers or parameters. Both of them will eventually converge, but the idea is that they both have benefits. Let's look at the applications of transformers. There are the applications of transformers are everywhere. In fact, these days they are even being used for images and computer vision, like all of those things as well. But let's look at the NLP and conversational AI. Translation, machine translation, which is a generative task. Automatic speech recognition, which is also a generative task. They're also converting speech to text or text to speech. Again, it's a sequence to sequence task. So there as well. Language models like summarization, text summarization, transfer learning, sentiment classification, like NLU, sentiment classification, emotion detection. And then you have NLP, which is topic modeling, ranking, search, text analytics, parts of speech tagging. In conversational AI, you have all of these. Conversational AI actually uses a lot of these things here and there, because you are building an experience on top of all of these things. So for conversational AI, you can use, for voice, for speech recognition, for language understanding, for dialogue management, for natural language generation. You can, for all of these things, you can use transformers. Now, we are running out of time, but I will just quickly give an overview of the two kinds of tasks in all of the NLP or Conv AI. One is decoding task, another one is encoder task. Encoder, as I told you, are great for classification or ranking kind of task. And therefore you will see this x-axis means complexity, that is more number of parameters. So you have BERT, distal BERT on the lower end. And then you have more Roberta, maybe better, XLM more powerful, Megatron even more powerful. And then you have this generative models. GPT-2, GPT were initial decoders, but now you have GPT-3, Turing NLG, these are more powerful. And there is this class of model, which is T5, which can be used for both decoders and encoders. So there are some models which are great for both of the tasks. So these are the two areas. And let's look at, so if your task is basically a generation, use these. If your task is encoding, use these. And all of these models are accessible via transformers, Hugging Face, and you can search. You can go to Hugging Face website and then search these models, and then you will be able to, you can see task, a variety of tasks. For each of the tasks, you will find various models which you can use for your own application. Now let's look at where the research is heading. We know what the current state of the art is. The research is heading towards more self-supervised and unsupervised learning. So you might have seen a few shot learning or zero shot learning through GPT-3. Those are the approaches where we can use, because these GPT-3 and these models are trained on billions of sentences with billions of parameters. They have literally seen almost every sentence or every sequence of words. So even they're not actually smart, these GPT-3 models, they are still dumb, I think. But what they're doing great, or what they're great at, is they're great at memorizing all the sequences. And because they've seen all the sequences, they're great at generating sequences based on the context. So I would say we have not achieved that kind of AI the way it feels like, but they're good enough for our tasks, the tasks that we deal with. And with these kind of complex models, these models can memorize almost any sequence and therefore can mimic the output as they see. And therefore they're more contextual as well, because based on the input in different scenarios, they generate different sequences. That is one, zero shot and few shot, which will require substantially lesser data. Another one is domain adaptation. You train there is this paper from my ex group at Alexa or Uber. I mean, this is my team here. But point is that Alexa recently came up with this paper called Language Model is All You Need. Essentially, you can now make language model much more powerful and therefore use it for conversational AI applications or NLP applications as well. It's like the idea of transformers is all you need, or attention is all you need, but more tuned towards conversational AI and NLP application. The idea is that you train on some domain, and with minimum supervision or substantially lesser data, you can still build the applications that you want. These are the two more self-supervised or unsupervised kind of applications. Now let's look at how I just talked about conversational AI. I talked about NLP technologies, but let's see how it can be used here. So again, another example of conversational AI, same components. There is speech, ASR, speech recognition. There is language understanding. There is dialogue management, and there is natural language generation. So there is an input. Given that input, these are classification tasks. So for here, which is domain identification, intent identification, and slot, you can use BERT, Roberta, because these are great classification models. Then you have dialogue management, which is also classification model. You can also still use some kind of BERT or variant of BERT for this thing, right? Or which are more encoding. But to convert this action into a sequence, which is a natural language generation task, you need a generative model. So such as GPT-3 or GPT-2 or maybe T5, those are the models that you can use here. And same thing here for ASR, speech to text, you can use generative models. So these are the models which I showcased in the previous slides. You can use them in these settings here in conversational AI. And this is the final slide, evolution of conversational AI. Conversational AI has evolved in 4 stages, level 0 or 4 or 5 stages. It's more like driverless cars in a way. So level 0 was rules and keyword spotting. That was in 1990s. So let's say if I talk to an agent, if I say movies, then it's basically based on identifying the keyword, and then based on that, take an action. Then came IVR, like phone tree style. There's a phone tree and fixed set of frames or frames. By the way, majority of conversational AI systems are still leveraging or following IVR or IVR style. You call them, they say press 1 to do this, press 2 to do this, and so on, so on. These are more IVR style. Then came IDSF model. This was from my previous managers. They were the founding, Gokhan Tour and Dialog Tour. They actually built this IDSF model, which is still state of the art, used by almost every company. It's called intent detection and slot filling. It was based on RNNs. And Alexa and Google, the previous version of Alexa was using it, and to my knowledge, Google actually is still predominantly this. Then came Alexa Conversations in 2018. I was also partly part of it, like was involved in some parts of it. But the idea is that these are level 3 Alexa conversations. Is level 3 because these are model based dialog manager. So if you look at here, there are 3 categories. One is rules based, second one is hybrid, but these hybrid are more annotation heavy. They require lots and lots of annotations, and therefore that makes them contingent of the data which is available. Alexa conversations converted, level 2 was mostly NLU being model, level 3 was NLU plus dialog manager being model as well. So level 3 was make everything sort of model based. Then we released something called Plato at Uber. It was somewhere like 3.5, where we made data more, we made this training more efficient through RLL, reinforcement learning and simulator. We could use them to generate more data or generate the data, which then can be used to improve the system. So this is more like 3.5. Around the same time, this inflection point came through transformers. With transformers, we are able to train in one domain and then adapt to varieties of other domains. And this was the inflection point. Rasa, which a lot of you might be aware of, Rasa also happened to be around the same time. And Rasa kind of made it, built open source tools on top of these things, right? So transformers and all of those things. But this was the key inflection point. And now things are heading towards, as I told you, unsupervised, self-supervised learning, which I'm part of at Got It AI. We are taking everything. We basically are saying you don't need annotations. Annotations can be obtained automatically. And once you have data annotations available automatically, you can train the model and then upgrade them as you wish. So it's more like moving towards driverless conversational AI system, or human, like minimizing human in the work or human in the loop. So that is the evolution of conversational AI. Now, I know it was slightly longer, but I'm open to any questions.
Thanks a lot. Thanks a lot, Chandra. So I see a question in the chat. Okay, so I see raised hands. Let me maybe first read questions in the chat, and then I will take questions of raised hands. So while I was asking, can we say that BERT is an analogy for CNN in NLU?
No, CNN, the question is CNN, Conversational Neural Network?
Yeah, so you can actually see the questions in the chat.
Okay, yeah. Can we say that BERT is an no. CNN is a neural network. BERT is also a neural network, but trained for a specific task, or trained for it's a language model. You can train a BERT-like model even using CNN as well. But CNN is you have multiple kinds of neural networks. CNN being one of those, predominantly being used in images or computer vision applications. RNNs is another category of neural network, which is used predominantly for natural language NLP applications, including conversational AI applications. BERT is based on transformers. Transformers is parallel to CNN and RNN, but much more powerful through attention. But the analogy would be more like transformers. What CNN is to image, transformers is to probably language, but still not the same idea, because you can use transformers for vision applications as well. BERT is, think of it like BERT is a language model. BERT is a language model which is trained to learn sequence of words. And now it is trained like a language model. You can use it for varieties of tasks. Let's take an example. As a human, if I know how to construct sentences, I can use it for varieties of tasks. I can use it for understanding what others are saying, because now I can generate sentences. If someone is saying sequence of words or saying something to me, I take it, I ingest, and then I understand, right? So that is the idea of language model. Once you train a language model, the same language model can be used for understanding what is being said, understanding the sentiment, understanding the intent, understanding any kind of action to be taken, right? So that is the application of language model, and BERT being one of those. BERT is a kind of language model which once you train can be used for tasks like these, like sentiment classification or whatnot. But CNNs can also be used for these things. It's not like CNN cannot be used. In fact, people have used CNN for training language models, but they are not apt, they are not best for language model tasks or NLP applications. BERT is much more powerful because it is training a language model. But you can still use CNN for language model. A language model trained using CNN, let's call it CNN-LM, that is synonymous to BERT. But as BERT is to transformers, BERT is based on transformers. CNN-LM is trained using CNN. That would be similar. A language model based on CNN and a transformer-based language model, they are kind of similar. Does that make sense? And NLU is understanding. NLU, NLP applications or conversational AI, they're all related in a way. But NLU, CNN typically is not used for NLU. CNN typically is used for images because the way they're designed. Okay.
So I see a question from Neeraj. So I'm curious to see how you see the role for ontologies like WordNet in the future of natural language understanding.
A great question, actually. So Neeraj, what's happening with ontologies is that now that BERT and GPT and all T5, all these kind of models have been built, 2019 was the year, 2019, 2020 was the year when, if you go and look at the ACL, NeurIPS, all these conferences, in these conferences, a lot of the papers were actually centered around ontologies and knowledge bases. So you will see knowledge based BERT, KB BERT, KG BERT, KB knowledge, KB conversational BERT, and so on. Essentially, the idea is that how can you leverage existing ontologies and existing knowledge graphs, knowledge bases for better natural language understanding or better natural language generation or better conversational AI applications. So that part is happening. People have done substantial work. In fact, if you search on Google or GitHub, you will find, even on other places, you will see like papers with code. You will see a lot of work done in the past 2 years in this direction, but it is not fully addressed yet. It is still growing field. People are trying to use and leverage ontologies and trying to find based on their application. In fact, I had got it, my team as well. We leverage a lot of these ontologies and knowledge bases, and we try to fit in somehow and try to use them within our conversational AI applications, which are based on transformers.
I will take the question from Mikhail. I see he's raised his hand. Mikhail, please feel free to ask your question.
Hello, everyone. Thank you. Thank you for the great talk. I have a couple of questions. The first one is, what do you think, is it possible if we just add more parameters to T5 or to GPT 5, 6, 7, and so on, we'll be able at some moment to achieve quality of open-ended dialogue, which allows such end-to-end model to win Amazon Alexa challenge or not? This is the first question. And the second question, I'm very skeptical about fully automating dialogue, because in dialogue we have a very unique situation compared to many other fields of AI, is that we still have no good automatic way to measure quality of dialogue. We always need to rely on humans to annotate and to evaluate conversation. If we are talking about open-ended dialogue, not about some in-domain conversation like booking or restaurant or stuff like that. Do you have any ideas how we can go beyond this burden of human evaluation? Thank you.
Both of them are great questions. I can just keep on talking on this. So the first one is basically what will happen if you add more parameters, GPT 3, 4, 5, 7, 10. First is that, and second one is automatic system for automatic conversational AI system, especially for open-ended. So let's take the first one, which is adding more parameters. Yes, by adding more parameters, we will make them even more powerful in terms of storing data, and we will make them even more close to zero shot. Zero shot, to the people who don't know, zero shot means if you pass some input, it will generate the label for you without even explicitly providing the label or training the model. So we will get closer to that. I can give an example of humans do it, but we will make them more powerful. But that does not necessarily mean intelligence. Intelligence is something different. And there's a big debate going on in the community for the past couple of years. Bengio versus Jan LeCun versus Marcus, whether what is intelligence, what is not. Deep learning is a tool. And I also think that I think deep learning is a tool. Adding more parameters will surely make it more powerful, more useful for our applications. Yes. In fact, the applications that we currently are involved in, yes, deep learning can be used, would be used. But is that the intelligence? It's a question. I do not fully agree with it. I don't think it's intelligence. It's just making them more powerful. It's like this. You can take something and just give many, especially the way we train with feed with the backward back propagation, extremely inefficient approach, extremely poor approach. I can give an example, hummingbird. If you look at hummingbird, I have a lot of hummingbirds in my house or in my garden. I mean, look at that small bird. Look at the number of neurons that small bird has, and that can remember thousands of flowers, and for many years, every location of it, right? And it does not require as much data. I mean, it does not. We look at these models, GPT-3, 1.75, 1 trillions of parameters. Look at their parameters is substantially higher than this a bird, but a bird is much more intelligent, much more powerful than that. Of course, it is not designed for the task. Their tasks are different, but intelligence is something else. Yes, with these parameters, more parameters, we can make them more powerful, make them do things which humans do, but it is extremely inefficient. Like one of the worst optimization, I would say. I mean, therefore, we are seeing a lot of the research work in trying to compress these models. Distilbert. There is substantial efforts going in the direction, and we will see best of both worlds. So then the next question is, second question is, one follow-up to the previous question is whether we will reach human-like intelligence. I don't think so. There is intelligence, or the way we have evolved, it goes beyond number of neurons. It is just not neurons. There was intelligence even before there was neuron, right? In fact, many species do not have neurons. Trees, they do not have neurons, but they're intelligent in many ways, right? So there is cell, there is memory, there is a lot of information going on there. So a point is that intelligence is something else, but it's still area of debate, and people are trying to understand that. We don't know the concrete solution yet, but the moment we get there, we will also be close to the source of creation as well. Now, coming to the second part, which is the automatic evaluation, I 100% agree with you that conversational applications, whether they are open-ended or closed, task-based, both require some kind of evaluation or some kind of human in the loop to make sure the quality is coming out to be good. And there has to be some way. Task-based dialog system there are some automatic ways of evaluation. People have done that. And there is substantial work. Even I have published a lot in that direction. But on open domain dialog system, I think I happened to be, when I was at Alexa Prize, we published a lot of work in how to evaluate open domain dialog system. So there are some ways through which we can mimic or can come up with better algorithms which can predict if given a question and given a response, whether the response is good or not, even in an open domain setting. And you can do that. There is work in that direction. Is that the best work? Don't know. Is it the area of research? Yes. Will we see more work in that direction? Yes, I'm seeing that already, and we will see more of that. But the idea is that, if with these kind of contextual models such as transformers, we will be able to make models which can account for context and therefore be able to evaluate whether a response is good or not given a question. So let's say even in open domain setting, if I say, what do you think of Obama? If your model is able to identify that you are a Democrat or Republican, or what your preferences are, or what your choices are, maybe this model would be able to either debate with you if it is designed to have different opinion, if it is designed to communicate with you in a very smooth way and trying to make it more longer conversation, then it will try to agree. Sometimes may disagree, but might try to agree. But what it will do is it will basically generate sentences based on what it has seen. So let's say if GPT-3 was trained on Reddit data or Twitter data, a lot of it, if based on the context, it knows that you are a Democrat, and if it knows that you probably are inclined towards the work of Barack Obama, probably this model will generate sentences or identify sentences from Reddit data which it has learned and then use them. So essentially the idea is that once it knows the context, once it knows the objective, based on that, it can construct the sentences. And that's what even humans do. When we speak, when we have debates, when we share our ideas, we try to understand others' point of view, which we call as context. Now we know the context. With that context, you can generate the response, and it's called conditional language generation. So you can make your models generate sequence or output based on the context. But to your point, yes, I agree with you that these are not the best approaches, because the moment you go open-ended or open domain, you are already saying that there is no task, and therefore finding these metrics or finding this context are simply hacks, but they are not the true intelligence or the true open domain kind of automatic systems.
So just clarify, because I understood Mikhail's question is that open domain questions is like impossible fully automate. There always should be a human in the loop. Like, do you agree with this, or you think it's at some point it could be fully automated?
I mean evaluation of the dialogue. So it can be automated. So to train system, you need to evaluate the quality. And the problem is that to build system, you need to evaluate quality. And now you can somehow evaluate, partially evaluate quality, but then you still resort to the human evaluation. This is why, for example, Alexa challenge is so important for development of conversational AI technology, because you can have a lot of human evaluation for this. And this is very, very valuable.
Yeah, I agree with you. And that was the design when we proposed Alexa Price. This is exactly what we came up with, exactly similar ideas. We came up with automatic ways of evaluation, but we also had human, which has hundreds of millions of Alexa users, which will then evaluate or give feedback. And with that feedback, we improve these models further. So basically, we are getting real-time feedback, but we're also using that feedback to improve the system further. But you're right. Without that feedback, we will not be able to get that kind of autonomous conversational AI system or autonomous dialogue system. We need feedback for that. We need that kind of data to be able to train models like these.
Thanks for question, and thanks for answering. So I see a question for Kirsten Zverina. Do you want to ask directly your questions?
Okay. Hopefully you can hear me. That was an awesome talk, by the way, and particularly some of the summary ones about the evolution of conversational AI. That was an awesome slide. It made me want to ask, when you were talking briefly about reinforcement learning and some of the changes that had brought, because I've been out of the picture on sabbatical for a couple of years. I'm kind of curious, what's the latest that you're seeing in that space in terms of reinforcement learning in machine learning? You mentioned changing the data, and that was giving a giant leap.
So okay, so is your question around how how reinforcement learning is useful and how it can be used to further advance the conversational AI application? Is that your question?
Partly on the comment. So I'm quite interested in that point you mentioned about basically mimicking life, not just the conversation. So not necessarily, I don't believe that intelligence is something that will be mimicked that easily, but the mimicking of life. So creating the hummingbird on its specific task, whether it's a conversation or not. How have you seen reinforcement learning changing what's happening in this space?
Yep. Great question. And in fact, out of all the algorithms or approaches of machine learning or AI, supervised, unsupervised, and of course, a lot of those. Reinforcement learning is that piece which is closest to evolution. In fact, the fundamental way reinforcement learning is, you get the feedback, you update your system. And that's how evolution has happened. And in fact, one of the questions from Mihail was, hey, we need human in the loop. That's feedback. And that feedback can be leveraged, can be used via reinforcement learning to further improve the system. So when I speak, I've spoken with pioneers, and they have been my managers. Zubin, for example, Zubin Gramani, he's pioneer in AI, one of the most cited persons in machine learning. So this, he was my skip level manager, and we have had many discussions. I've had many with them. Point we eventually conclude is that when we say AGI or artificial general intelligence, or making them as close to humans, the closest tool is reinforcement learning. Now, currently, reinforcement learning has even dominated or has taken over by deep learning community substantially. But as I mentioned, deep learning is a tool. Today, we are using, and within deep learning, we had CNNs at some point, neural networks, RNNs, now transformers. These tools can be used. Tools will change. We might have more sophisticated tools. GPT-3 can be used, or a lot of these things could be used. These are tools, but these are not the approach. Reinforcement learning is the closest approach. It can use all of these tools, right? So it can use transformers, it can use GPT-3, BERT, all those crazy models. But the real intelligence is in this approach of leveraging feedback, take that feedback and improve the system. And that's how the entire evolution has happened. And that's how, I mean, even I personally try to see that with a lot of species around me. I see that. And if you read a lot of this, how evolution has happened, you will find the closest being reinforcement learning.
Lost signal at the end there, but thank you very much on that one. And my second question, if I'm allowed to ask it, I think was being touched on with the answer to Mikhail's question, which was about what could be done when you're adding context more. So VR and AR, say for example, to a situation of trying to assess something in terms of conversational learning. I found when you're putting out more mechanisms like here with images or whatever, it's easier to understand.
Yeah, so there is this big field of multimodal AI coming in, and we call it embodied understanding. A lot of work done in the past 2-3 years. I also happen to publish some work in that direction. Idea is that I can give an example quickly. If multimodal, let's take a multimodal example. Let's take humans. Humans have varieties of senses. They have eyes, right? We have ears, we have a voice as well, and touch and whatnot. So let's say if I see an animal, which is, I'm not able to differentiate whether it's a fox or if it's a dog or if it's a wolf or it's a husky. They're very similar, right? Even some of the best models, even humans, they fail. But the moment they create some kind of sound, I will be able to identify it's a fox, it's not a dog, or if it's a wolf, it's not a husk, right? So, or husky, sorry. So the idea is that when you tend to have more inputs, your understanding becomes, you get more input, and therefore your understanding is better. And that is what is being dealt with now. People from computer vision, they're coming into understanding language. People from language community, they're understanding images. And there's this big embodied or multimodal AI happening. In fact, that was also motivation of, when we created a multimodal lab at Uber AI, that was exactly the same motivation, with more modalities, with more kinds of input: speech, voice, speech, text, language, vision, right? With all of this, even touch, with all of these, which is perception also. When you combine all of these, you make your AI much more smart, much more powerful. And that is what we do. So to your question, to your question, a lot of work is happening right now. So if this is something which interests you, look at the latest work from Facebook AI or Facebook Fair Lab is doing a lot of work in that direction. DeepMind is doing some work in that direction. Alexa is now these days is doing some work in that direction. Even to be able to understand, even for communication, multiple modalities leads you to better understanding and therefore better quality of communication.
Thank you.
So basically, to your point, do you understand correctly that basically the future of research in NLP, NLU, and would be including those multi-models? Is
Yes.
this where research is going?
Yes. That's what is happening, and people have understood this thing, and therefore language people are using vision for building better applications, and vice versa.
Mm-hmm. Thank you, and thank you, Kirsten, for your questions. I see questions from Adam. Actually, we have 2 Adams here. Okay, well, let me first read the first question from Adam that he posted a while ago. So, from the final slide with Got AI Tech, I get it that you don't want to share exactly how it's happening. I don't know if you want to share, Chandra, more about work that you're doing now. And the next sentence, do you think for goal-oriented tasks, it should be some sort of combination of reinforcement learning simulation with zero or few shot learning?
So yes, let's take the first. Of course, I cannot talk a lot about this because there are patents involved in this. We have built a tech which we think is it's a new leap. But again, I cannot share a lot of those information. Second thing is, but I somehow left some of the ideas which will give you actually some ideas on zero shot learning or stuff like that. That might give you ideas of how it can be done. Now, coming to the second question, which is reinforcement learning. So reinforcement learning with few shot, where is that field going, and how will that impact conversational AI? I see a lot of work these days happening in reinforcement learning. In fact, the Plato dialog system library, which we released on GitHub maybe 2 years ago at Uber, that one actually is heavily based on reinforcement learning for generation and simulation and whatnot. The idea is that, yes, reinforcement learning is being used. So reinforcement learning with combined in combination with GPT-3 or transformers can help you generate more data. And therefore, once you generate this data, and if you build some kind of approximate evaluator, then you will be able to complete the loop. In fact, there's a good paper from my group. I can share that paper in the channel after this, which will give you a good insight of how reinforcement learning is using these transformers or these generative technologies for more efficient sampling, and therefore better approaches, like better results. So typically you require, to train a good NLU, you require thousands of samples at least, depending on number of intents and whatnot. But with these things, you can reduce the thousands or tens of thousands to maybe a few hundred, or even few hundred to maybe even few tens, or maybe even just 1 or 2 examples. That is the idea, essentially. You can use reinforcement learning. You can use simulators to generate the data. Simulators can use GPT-3, T5, these kind of models. And then you can have a reinforcement learning model along with evaluator model, which will then help you further improve your system. So once this is trained, the core is trained, then you will need only a few examples to update the system. That is the core. And in fact, that is also very close to what we do. But that is not the full picture. The conversational AI goes beyond that. You have to account for many things apart from these technologies like RL and evaluation and simulator.
Thank you. So I see a question from Adam Williams. So basically he's asking, wouldn't be a closer approach to intelligence be reinforcement learning combined with a genetic algorithm? How would this be utilized in a conversational setting?
People have done some work. In fact, reinforcement learning in combination with genetic algorithm has been a good research area. I've seen a lot of work. Not more recently, I've not seen that. Like, I did not happen to look into that. But one thing is, there is this professor. He was my peer at Uber, Jeff Kloon. We used to work together. We have done some work together in this direction. So if you're interested, we have published a paper. I can share that again. It's based text game. We basically have built models using reinforcement learning to play games via text, or text-based games, and we try to explore some of these areas, RL with genetic algorithms and how to improve it further. That is one good area. The problem with reinforcement learning is, and I'll tell you the biggest problem of reinforcement learning which we are facing right now, extremely not robust. You need to tune them so much to make them work. That is a big challenge. Once we solve this problem of making them robust, then we will be able to address then we will be able to take reinforcement learning to the next level. And there are people who have done research in this direction to make reinforcement learning much more robust, less fine tuning, less parameter tuning, because evolution might not have happened this way, or maybe we don't know. But one problem that we're seeing with reinforcement learning is if it works for one setting, it might not work for another setting. You have to do a lot of tuning and tweaking and whatnot. So that is not, again, real intelligence. If we maybe with algorithms like meta learning or those kind of approaches, yes, with those approaches we are addressing some of these problems. But once we crack that code properly in different applications, then we will be able to leverage RL and genetic algorithms for more applications such as conversational AI. But I still think it is still area of research, but it's far away from product applications.
Chandra, I have a question. So, for the last maybe 5 years since, neural network are sort of dominating research area, we sort of fixated on neural network in terms of achieving sort of AGI. But what is your approach? Do you think there could be something else beyond neural network approach? Maybe there's some other research going on, right? That takes like completely different approach for achieving AGI.
I would say neural network has helped us achieve so much. You cannot make changes overnight. Community is aware of the changes that are required, and therefore they're pushing the boundaries. There's already a good communication or debate happening whether deep learning is the way, neural network is the way, or maybe more evolutionary technologies is the way. Jeff Kloon is one of those, actually. Now he's at OpenAI. So there is substantial amount of research happening in this area. But to me, if you ask, I see one immediate problem which can be fixed, which addresses a lot of these things, is backpropagation. backpropagation is extremely inefficient way of training neural networks, extremely inefficient. We can make it substantially more efficient. First of all, it is cubic polynomial. You can make it more linear. And it's like the reason why you have to provide thousands of examples for just training a dog, identifying if it's a dog or not, it's because of this bad algorithm. And we need to fix it. But no one has, people have not thought about, people are not investing a lot of time in this, because currently the research has become, hey, you know what, this is a task, this is data. My model beats your model. You got 90% accuracy, mine got 95. The papers are getting rejected plainly, even if they have great ideas, new ideas, but because they had 70% accuracy with new approach, which is out of the box, they are just getting rejected. This is a very bad mentality in the way, conferences, the top conferences are accepting the paper. I do not like it. That is something which I would want to change. But good thing is now, Benji, Jan LeCun, a couple of people have come up and they've raised this problem. And now they are not just going by leaderboards or performance, they're going by novel ideas. So that is one change. One of the change which I'm seeing, in fact, I advise a company, or I happen to be in contact with them maybe a few months ago. They are changing this, fixing this backpropagation problem. Once you fix it, then you can make it better. In fact, the problem is not with neural networks, because even the way humans and the species have evolved, they leverage neural network. In fact, the idea of how we come up with neural networks comes from that. Like the artificial neural network leverage the idea of how human, or the species that we have, they have evolved. The problem in learning and training, humans don't train, they don't require that much data, they require substantially lesser data, but these machines require substantially orders of magnitudes more data, and that problem has to be fixed. It's because of the way we train them, the way we learn them, make them learn, the algorithms, the underlying algorithms, that has to change. And I'm seeing that people are doing some work in that direction. In fact, I've seen a lot of great results in that direction. So we will see more of that in the coming 5 years.
Like, if we want to stay, tuned about this, what resources would you recommend to track? Is there like any websites or like conferences where those novel ideas are welcome?
Great question. I do not have one answer. I mean, I don't have one source of this one. I usually tend to follow people, different kinds of people on Twitter and LinkedIn here and there, and I read papers. I by the way, I review papers and conferences like these ICML, NeurIPS. So I encounter these papers. So I'm always interested on these kind of papers, less on the BERT or GPT-3. Those are natural incremental improvements, but I'm more inclined towards reading these kind of papers. So the best way is to read papers, and there are some. By the way, there are some. Nature is one journal. There are some journals on evolutionary technologies, right? If you try to read more on those, you will get more of these philosophical ideas, not philosophical ideas, more practical again these days, and you will find more of those. But there is a lot of good conference and journals these days coming up. You can follow their research.
Thank you. I also wanted to get your opinion on one thing. So, like what's happening in research right now, like especially when you were describing GPT-3, that you're adding more parameters, you're bringing more compute. But do you think like increasing compute is the way to go in terms of, again, towards AGI? Like, let's say if you have limits, in terms of your compute, would still be chance like possible to move towards direction of AGI?
I think that is one approach, but not the full approach. We need more parameters to understand what can be done, but they are highly inefficient. So we need research in the opposite direction as well, how to make them smaller, to make them more efficient. And we need third line, we need 3 lines. Add more and more compute, that is one, which is already happening, GPT-3 and T5 and whatnot. Second one is how to compress these things into smaller one to make them more practical. And third thing is, third direction is to trying to, the evolutionary algorithms, trying to see how nature has evolved and try to mimic ideas and then bring them back into these things. So let's say, even if we take an idea and in quanta, if you look at quantum is much more efficient. I think we have not reached I personally think that we have not reached the limit of computation. We have reached the limit of computation that we know or that we have tried so far. There is a lot of things which we don't know yet and which are still areas of exploration. One of them is quantum, right? Quantum mechanics and quantum computation. and a lot of other variants as well. Even as I told you, backpropagation is completely inefficient. You need to find better approaches because that's how humans and species are learning. So there is this third area as well, without which we won't be able to go much long. And once we identify new areas in this third field, which is evolution and newer areas, such as quantum computing, we can take those ideas and then bring to the first two areas, again adding more parameters and then scaling it down. So I think these three things, these three fundamental pillars, will eventually help each other towards AGI.
Thank you. So I see a question, like a raised hand from Vinay. Vinay, do you want to ask your question?
Yeah, hi. Great talk. So my question is around grammar-based architecture. So we understand that grammar forms a very crucial part of generating good sentences, and even like all the text that we have has underlying grammar within them, right? There hasn't been much work in terms of conversational AI or NLP in general when it comes to integrating grammar-based architectures such as and/or grammars or similar grammar architectures in deep learning. So I would like to know what are your views on that. Is there any scope in this direction? Are there people working in this direction?
So it's not like grammars have not been accounted for or have not been used in conversational applications. In fact, before deep learning, using semantic graphs, syntactic graphs, parsing, syntactic graphs, parsing, semantic parsing was the way actually. That's how people used to do. Even in machine translation, converting one language to another, we used to use lots and lots of grammars. Now we are not using this anymore because we have found out that grammar is function of one language. Grammar will change based on different languages, but the underlying sequence, which is language model, does not change. That is same. So what we have done is we have found a more abstract way. If you look at grammar is creation of some rules that we have come up with. There are, humans might have been communicating without grammar for many years, right? So grammar is a set of rules that we have created, which limits the capability of conversation, actually, if you will say. However, it is also the way to put your language, put your ideas in a better way. Yes. But the idea is that it is also limited. I can give an example. If you look at the other languages, Sanskrit, for example, Tamil language, some Russian languages, some of the Eastern languages are much more powerful. Even some European languages, which German, which has compound sentences, they are much more powerful. There is no notion of, if you look at, I might make a controversial statement now, but if you look at some of the Eastern languages or some of the European languages, they have this notion of having a human being labeled as either he or she. You don't need to. There are some pronouns which are beyond he and she, but English, on the other hand, is not the case, which we know. We are seeing the problems, and it has not been designed for that, and that is because of the grammar. If grammar is a set of rule which is designed to serve certain population, but is that the best thing? No. There are more abstract ideas which account for even bigger things, and that's what is happening with language models. Language models are not. You can feed, if you feed grammatical knowledge or parsing or the ideas which you mentioned in there, they will make you perform better, probably. Yes, of course, because you're feeding additional knowledge, but that can also be done via ontologies and knowledge base. In fact, your language model can learn the language or grammar automatically, because it will learn, okay, given the language is English, this is how the grammar looks like. Given the language is, let's say, Chinese or Mandarin, it will learn those logic already. So the idea is that grammar limits, language model expands, because it's much more. Any language having grammar, I mean, if you take any language is nothing but sequence of words or sequence of phonemes or sequence of frames, and that's at that level we learn language, neural networks or transformers or whatnot, which is more abstract, which is a superset of grammar. Does that make sense?
Yeah, it does. But my question was more onto, I'm not specifically talking about the grammar of a particular language, but even in the way we construct sentences, right? Whether we know the grammar of English or whether we know the grammar of any Eastern languages, there is an underlying way to construct the sentences, right? That doesn't have to specifically follow grammar of a particular language. So I'm not. So if you take the example of and or grammars, right? So these does not have any binding to a particular language. These are abilities to construct conversational sentences. So my question was more in terms of, so if you look at GPT architectures, right? They are so huge, so many number of parameters that they can just remember all those things, right? Is there any way to maybe make a more streamlined way of learning through grammars, which can have lesser number of parameters, but still as generalizable as GPT-3?
Yeah, you're right. I mean, that's a good area to explore, a good research area. Actually, you can publish, if I don't know at what capacity do you work, but if you are a researcher and if you want to do it, I would highly recommend do it, because this is also a good idea how to make them more efficient. Currently, the reason why we need more parameters and more data is probably because we are not leveraging our ontologies or our grammar rules, or the example and or example that you gave, and in fact some of the rules that we already have. If we feed them, maybe we don't need that much data. But the thing is, it is still not close to intelligence, I'll tell you, because someone has written those rules, right? Someone has written those kind of grammars. So it is more like metadata provided to the models. The moment you provide metadata, then you do better predictions. It's like the example of multimodal. If I know Harry Potter with a device with screen or without screen, I might be able to do much more better performance. I might have better performance on classification task or prediction task. Same thing can happen with grammar, because there is some kind of logic already. If we feed them efficiently in neural network, that will actually lead to minimize number of parameters and data. So I would say this falls under the second idea, which is, can we make this training much more efficient? Yes, we can with these grammatical rules, because that is additional information which is available. You don't need to learn it with so much data. You already have those things. So yes, I think it's a good research area. Someone should look at this.
So I see a question from Adam. Do you have any thoughts on controversial paper, Reward is Enough, published by Silver from...
Yeah. So it's a big debate going on. Both of the sides have their valid points. Reward is enough if we see in a way, yes. I mean, I do not fully agree with one or the other. I see both of their points being valid. Question is just saying this will work is not the best approach. Yeah, and in fact, you might have seen that I've been saying this many a times, that adding more parameters is not just the way, but that is one research area which we should continue to explore. Same thing is with reward is enough. Just saying that reward is enough does not simply gives you an AGI solution. We know that reward, and we have known there has to be a primary motivation. In fact, that has been the fundamental reason, main central point of reinforcement learning as well. Reward is enough, and that's how the evolution has happened substantially, yes. However, there are a few things which goes beyond reward that I personally think. But if you're proposing this idea of reward is enough, you also need to provide a robust way of how will we make this happen. So from idea point of view, it's a great idea. We should explore, and we should try to make it much more efficient. As I told you, that reinforcement learning these days it has been extremely not robust. The variance is high. They're very hard to tune. If we can come up with a more robust approach where we can leverage this idea of reward is enough, I think that's a good area. So to me, if you were to ask me, I would say it's a good area. We need to think deep in this one, but we also need to build and come up with more efficient approaches or algorithms which can leverage or which can explore this idea of reward is enough. Currently, we are not there yet. Currently, it is extremely inefficient or not robust.
Mm-hmm. Thank you. I think we can wrap up our conversation for today. Maybe later, Chandra, if you will be able to share more about your current work and your current research, we can make another meetup and then learn more about what you are working these days.